You're good, Jeff.
Thank you. Good morning. I'm Jeff Hammond, Executive Director at International Ground Source Heat Pump Association. Thank you for joining us for the January IGSHPA Dig Deeper webinar. We have Gaylord Olson as our speaker today. Before we get started with Gaylord, we have just a few announcements so that we bring everyone up to date on the latest happenings at IGSHPA. All right, so this webinar is one of two. We have our town hall, which is a broader topic, and the Dig Deeper is more technical. We are still accepting abstracts for the 2026 webinars. If you're interested in speaking, go to the Training and Events button right on the homepage at IGSHPA.org. You'll find abstracts there. And we're also still accepting advertising for these webinars. Since they're recorded, it's a great way to get your name out there because it's going to be uploaded to IGSHPA's YouTube page and on the website, which allows you to have your logo on there for quite some time. I want to make sure everybody saves the date for our annual conference. It's coming up soon in April. This year it is in St. Charles, Missouri, which is the St. Louis area. We have all the registration information, hotel reservations, sponsorships, exhibitors, all that is online now at IGSHPA.org. We couldn't do these conferences without our sponsors. We really appreciate all of the sponsors so far. As you can see, we have quite a few, but we have also a number of open spots. And this is also a great way to get your name out there. We continue to announce sponsors at each of the webinars and, of course, in all of our mailings. If you're looking at exhibiting at the conference, you'll want to make sure and act pretty soon. There are only about 10 spaces left. And of course, they're 10 by 10 booths, or they can be combined into 10 by 20. All of the 20 by 20 are used up and are spoken for, and all the tables are already confirmed as well. But you can see here we do have some spaces open. So you want to act fast on that. Our research conference, which is every other year, is in Vienna, Austria this year in late May. That information is on the website as well. Our last one was in 2024 in Montreal. And generally those are, like I said, every other year. We would love to have your help on our databases. We continue to add in more projects so that when people are looking for other similar applications, they can find them in the project database. For example, if somebody wants to look at how many government buildings or how many churches or what have you, those are going to be easy to find, or by geographical area. The other database that we can use your help with is licensing and CEE requirements. You're certainly the ones on the ground, you know this information. So if you could add in that information, we would be very appreciative. Our Geo Outlook magazine, you saw in our last issue, last July, we had a new format. Hopefully you like that much better. That was based upon member comments and suggestions. Our next issue will come out next week, and that will be the February issue. This is a preview of it. You can see the front page with the Missouri Botanical Garden application right there on the front page. So look forward to look for that in your inbox next week. We should be probably midweek next week. For CEUs, for your renewals, if you would put your name and email in the chat or the Q&A, and we'll keep track of those for you. There's also another option. If you happen to be watching this webinar as a recording, simply use this webinar code when you send the information to info@igshpa.org. If you're attending this live, this code isn't necessary. Just put in your name and email. But if you're watching this as a recording, you will need this code in order to get credit. Just some housekeeping, and then we'll be ready to start our presentation. So if you have any questions during the presentation, I will read those at the end. And just put those in chat or Q&A, and depending upon our time, Gaylord will be able to answer those for you. If we don't get to all the questions, we'll follow up later on. As I mentioned, this session is being recorded and will be uploaded to IGSHPA's YouTube page and on the website, so you can watch this later on if you missed anything. In the chat box, sometimes you'll get a window that looks like this, and that's because of security settings. Sometimes organizations have security settings for the ability to use chat. So you may get a window that pops up like this. You'll have to click OK to allow that to happen. If for some reason you can't use chat, just use the Q&A. We've enabled that. If you can't use either, raise your hand and I'll unmute you so that you can ask that question. Most people can use either one of those, so that's worked pretty well for us. Just a quick disclaimer and conflict of interest, and then we'll be ready to get started here. The upcoming presentation represents the opinion of the presenter and does not represent any official position, opinion, or endorsement of any products or services by IGSHPA or its members. IGSHPA town halls and Dig Deeper webinars are for member updates and education on the latest information in the geothermal heat pump industry and are not meant to endorse one technology or brand over another. It is the presenter's responsibility to disclose any conflict of interest or position that may arise in the content of the webinar. All right, with that, I'm thrilled to announce our speaker today. Gaylord Olson is an independent consultant and inventor with engineering degrees from South Dakota School of Mines and Technology and UCLA. He is a member of the Industrial Advisory Committee for Mechanical Engineering at Temple University in Philadelphia. He is the inventor and co-inventor of 12 patents, with several recent patents related to multi-source heat pumps, underground thermal energy storage, and solar thermal energy collection. He's a member of the International Ground Source Heat Pump Association, New York Geo, ASHRAE, the American Solar Energy Society, and the Northeast Sustainable Energy Association. Thank you so much, Gaylord, for presenting. I'm going to switch over to Gaylord's presentation now and turn it over to you. All yours, Gaylord. Thank you so much.
Okay. Is my audio still coming through properly?
Audio works great. Yes, thank you.
Anyway, the first slide here indicates that I've had a lot of help from an associate, Dr. Yao Yu in North Dakota State University. And he and I published a few things that you can track down and look at if you want. And some of the things presented here are jointly done by both of us. Move along to the next one. Okay, here's a list of sources. If you want to consider a multi-source heat pump rather than just one source, we think that there's a pretty good promise for that. Today, people think they have to choose one of two. They can either choose air source or a ground source. And I think the future might be better if we consider multi-source. And so these are three major categories of sources. The top two there, borehole deep trenches. Almost everybody listening or watching this would know about those, and maybe most of the others too. Notice at the bottom left, solar thermal, and the bottom right, air to liquid heat exchange. Many of those, actually, I think 4 of those are in common. They will do both solar thermal collection and air to liquid heat exchange. So those give an extra benefit that way. Move along to the next one. I'm going to have to go pretty quickly because I try not to run over time. I've thought about major categories of multi-source, and I've come up with 4 different what I call levels. So the simplest level of multi-source is where you choose one or the other. In other words, you can have an air source mode or a water source or ground source mode. Going into, in our case, we're proposing that we always have a water source heat pump as the basic element for that, with has the compressor refrigerant loop in it, and the multi-source approach then is how the water comes into the source of that heat pump. So basically, really simply, you could have just a choice of one or the other of 2 sources, or even 3. But that's not the only way to do it. Level 2, which we'll go into in a lot more detail here, is where one source, like solar thermal or dry cooler, can feed either warm or cold water into the rest of the system. So we're calling that preconditioning, but the people in Europe are calling that regeneration, but it's all the same thing. And it's almost obvious that we shouldn't have to be restricted to only one or the other of those levels. We can have another level, level 3, which in one system, we can choose whichever is best at the time, either level 1 or level 2. Now, there's still a disadvantage of level 3, and I'll explain that later, but it's written in words here at the bottom. It requires not only one source water pump, but 2. And then there would be 2 regions underground, and you keep one as warm as possible all year long, keep the other as cold as possible all year long. So that we're just calling level 4 here. Move along now. So these are just 3 very similar examples where it's multi-source. We could have used the word source instead of loop there, either way. But this would be multi-source level 1. I think that's pretty self-explanatory. Now, instead of only 2, the next slide shows 3. Now, it's kind of interesting that we think there's a good promise for having 2 loops underground rather than 1. And one of those loops could be used specifically for solar thermal and air to liquid heat exchange. And I'll explain that further later on. So moving along to the next one. Now, here's the leading headline for a company in northern Germany called ThermSelect. They are one of the few commercial multi-source heat pump companies. And they've been around for quite a long time. And they claim to be the world's most efficient heat pump. Now, that's kind of a bogus, meaningless phrase, because you might ask them to get highly efficient. Now, they're using their systems only for heating. Northern Germany doesn't need hardly any cooling. So only for heating, most efficient. So you could ask them, what's the average source temperature that they provide for their system? Or it would relate to the COP or seasonal performance factor. What's the best they can do? And they would give you some answer, and you would respond to them, well, I could do something better than that. Very simply, if you want heating, you can have a very large solar thermal array, very large water tank, so you can have water temperature for your system, pretty much whatever you want. The only problem is somebody has to pay for it. So it would be more meaningful if they could claim that they're the most cost-effective heat pump in the world. But I don't think they can claim that. So moving along. Now they say 2 renewable heat sources. On the very bottom of that previous slide, they said 2. Now this is on that same page. When you scroll down, you get to a picture of what their system can do, what it consists of. So move to the next one now. And here they're saying not 2, they're saying they actually have 3. So it's a little bit confusing that way. But if you look at the very top of this picture, they have solar thermal collectors on the roof, and they got a number 4 item on the wall of the building, which is an air to refrigerant heat exchanger, not air to water heat exchanger. And then they've got a number 2 item, which is probably a computer and controlled human interface box. The number 1 box they show there is where the compressor is, etc. So moving along to the next one, this is just a list of the dates that ThermSelect puts out as to their news items. And they have one going back to 2013, so they were obviously in business prior to that. And then there wasn't any news until 2018. Then 2018 was a very big year for news. They've got, I guess, 11 news items from that one year. And from 2018 until now, they haven't had any further news. Um, and they're still a very small company. And the only reason I can think of is maybe they're just too expensive compared to the competition. So now they do have a patent, or the founder of the company has a patent on his specific configuration. So it's possible that they haven't got to the point of mass production to have a low enough cost for that. But speaking of patents, for full disclosure, some of the things presented here are also either patented or patent pending. Move along to the next one. So I put a question into an artificial intelligence agent. I believe it was perplexity.ai. What examples are there of commercial multi-source heat pump systems that use both air and water as sources? And I was actually surprised. It came up with 5 different um, items, all from pretty well-known companies. You can see the list right here. And maybe some of these are not available in this country. They might be available elsewhere, but they're probably all the level 1 type of system where you could choose either air or water, or maybe in parallel. But I'm pretty sure none of them have what we're calling levels 2, 3, and 4. So I hope to be at the AHR event coming up early next month, and maybe I'll visit these companies and see the details on these particular so-called multi-source heat pump systems. So moving along to the next one. So this is goes back quite a few years in time. Let's see. I think it is about 10 years old now. Oh, we have a list at the end of this talk. There's a list of references, bibliography, and you see the number 1 there at the bottom of the page here. That means it's the first listed reference at the end of this talk. This was written. This was not actually built. It was theoretical, and the authors are all from Belgium. But I found it pretty interesting, and I'm a little bit surprised that I'm not aware of anybody who has built anything quite close to this yet. But this is what we're calling level 2. It's only preconditioning. The dry cooler can put hot water into the left-hand ground loop whenever the air is warm enough in the summer. It can put very cold water into the right-hand bore field whenever the air temperature is cold enough. So then in the summer, they can use the cold water going into the heat pump. In the winter, they can use the warm water going into the heat pump. Now, if you notice on the left-hand block diagram here, this is the summer. They're not even using the heat pump and compressor. They're bypassing it, the economizer mode. So that is a very efficient way to get cooling. If you can do it, you have to have temperatures in the range of, I guess, 35 to 45 or 50 Fahrenheit. Then you do not need to use the electricity going to a compressor. So moving along, I believe. So here's an example that was published in the IGSHPA Geo Outlook back in 2019 by Ed Lorenz, who's one of the trainers for IGSHPA. And he had a problem with his ground heat exchanger because he's in, I believe it's Winnipeg, Canada. And every year it was getting colder and colder and colder. It got down into the 20 degree Fahrenheit, 26 or 28 degrees Fahrenheit, and it was getting towards failure. So he could have called in a driller and drilled a lot more, some larger number of boreholes, but a less expensive way that he found to do it was to put unglazed solar panels on his roof. I believe only two of them. So now he's got two water pumps there and a heat exchanger. So on all the warm summer afternoons, uh, he's able to pump very warm water into his ground loop. So after he set this up, then every year his ground loop is getting warmer and warmer, not colder and colder. So that was a pretty inexpensive way for his problem to be resolved. Now, I I'm not sure what he would say if somebody were to ask, would it have been better to do this right at the initial time of installation rather than afterwards? But it might have been better to do it that way. So moving along, uh, a way to get to an optimum borehole size is to do multiple TRNSYS simulations over a long term and determine if uh, you have a limitation due to the cost of the boreholes, or do you have a limitation in the total cost of ownership because of higher electricity use? If your borehole exchanger, that is BHE, borehole exchanger length, is too great, the simulations will tell you that you're spending too much money drilling boreholes. On the other hand, if you don't have a borehole length long enough, you will have a lower average coefficient of performance, higher electricity bills. So the total cost of ownership is now limited by electricity use, not the length of the boreholes. So there's an optimum point. And this is reference number 8. You can read about it by people at Cornell University. The optimum length they found was 750 feet. So now if you think about this type of study, it can be carried forward to a multi-source system. I think that's what the next slide might be getting to. Yeah, so this is just a format for a graph that you can think about if people were to do simulations with a variable size ground loop and a variable size dry cooler or other type of solar or air to liquid exchanger, there would be only one point in this two-dimensional graph where the total cost of ownership would be minimized. It's not going to be simple, but at least it should be theoretically possible to get to that single point where you get the best result in terms of long-term cost. Moving along. These are 3 older examples of different multi-source approaches, all from Europe. The left-hand one is an example done by authors in Spain, and they put every single thing in one box. They've got a ground interface on the bottom left, boreholes, ground loop. They've got an air to refrigerant heat exchanger at the top. They've got 2 other heat exchangers, one for domestic hot water, one for heating and cooling, space heating, space cooling, everything in one box, which would have to sit outside. And they actually built a number of these, but for one reason or another, it was not commercialized. I'm not sure of the details, but anyway, that's reference number 2. Reference number 3 is an example of what we would be calling a level 3. It's reference number 3, but in terms of the 4 levels defined earlier, it is also level number 3 because they can have an either or choice there. They've got boreholes, they've got solar thermal collection. With the valves that they have, valves and pumps that they show, you can have either the boreholes by themselves feeding to that heat pump, or you can have the solar thermal by itself feeding to that heat pump. That would be what we're calling level 1. They can also do preconditioning from the solar thermal into the ground loop. That's what we're calling level 2. Now, let's see, let me think about this. No, I'm sorry, level 3. Pardon me, I did the wrong level. This would be level 3, where they have both the ability to do preconditioning and the ability to choose one or the other source. And this was a theoretical study done by people in Italy, and I'm not sure if it was actually built or not, but it looks like a pretty good design to me. The bottom is a very coarse example, again, of just level 1. They could choose an air heat exchanger or a ground heat exchanger going into a box that they're calling heat source hydraulic, then a water source heat pump after that. So this was people in Germany, I'm pretty sure, but you can read the details, reference number 4. Moving along. So it's interesting that 3 of the examples that are described in the previous slides all show almost the same thing. With the use of 2 different sources, they can reduce the bore field size by a factor of 2, essentially a factor of 2. In other words, they only have to drill half as many boreholes to get the same result as compared to conventional geothermal. So it's a little more complicated. They have to have expense for the second source, but it looks promising to me that this might lead to something fundamentally better. So moving along. So this is a very new publication. It was actually available on the internet about, I think, 2 months ago. But the publication date officially for the print version of the journal at the very top is 2026. So it's kind of hot off the press. Now they have the terms regeneration and bivalent. So regeneration is what we're calling preconditioning or level 2. Bivalent is the either or choice, level 1. They did not get to as far as level 3, where they can have both of those choices in one system. But you see the 3 authors there. 2 of them are based in Norway. One is currently based in China, but he did spend time in this country. And coincidentally, he spent time at North Dakota State University, where my associate, Dr. Yu, is located, but they were not there at the same time. So I found that an interesting coincidence, at least. So moving along to the next one. So I have the next set of slides are all from that reference that we just discussed. This slide shows what they would call a baseline conventional geothermal approach to heating and cooling of building. And they're showing domestic hot water supply also at the top there. Now, their design was for a multifamily building in Oslo, Norway. So they were almost exclusively needing heating for that building in Oslo. It's a 4-story building that I believe has 24 separate units, living spaces. So it's a medium-sized building, of course. And we can move along now. So this is the first of 5 multi-source approaches that they studied and quantified. So this has an air source heat pump and a ground source heat pump and you can choose which of those you want. And so now you've got to pay the money for two different heat pump boxes. So you've got to make that up somehow. And the question is that a more cost-effective way to do multi-source or not? And that's part of the study that they were aiming at showing. So moving along to the next one. So here's another of the 5 multi-source approaches that they studied. PVT, photovoltaic thermal. It's unglazed. And so it acts pretty much like an unglazed solar thermal panel, the same kind that Ed Lorenz used on his roof, except in this case, they're getting electricity generation whenever the sun shines. So that's a significant advantage. Most of the companies that make these things, I think, are based in Europe now, and maybe some in China. But I'm not aware of a source in this country. I could be wrong, but whatever. So moving along to the next one. Oh, this is conventional solar thermal only, and I believe they consider this to be a glazed flat plate collector, which is pretty common. And we have those manufactured by at least 1 or 2 companies in the United States. So again, this would be what we're calling level 2. That is, they're doing preconditioning with this. Same one on the previous slide, actually. So moving along to the next one. I'm kind of rushing along here. Oh, I should have mentioned that a lot of the older items that we're covering here are available both through the IGSHPA website and also through YouTube. If you go to YouTube and put in, it's at YouTube, you put in IGSHPA and November 2022, you will get an earlier version of this talk. And so I'm kind of going over those kind of quickly. What we're looking at here now is totally new, not available in 2022. But to get a complete picture, you probably would be well advised to go and take a look at that previous video that was done, November of 2022, IGSHPA. So moving, let's see. So what here we have a dry cooler and boreholes in what we're calling the level 1 approach, either or bivalent in terms of European terminology. And there's just a valve to select one or the other of those sources, air source or ground source, water source, heat pump. Pretty straightforward. So moving along to the next one. This is also a dry cooler in combination with a ground loop, but this is level 2, not level 1. It gives preconditioning capability, regeneration in European parlance. But you notice also there's the valve. The valve B1 can either allow the water to go through the dry cooler and then in series with the ground loop, or it can totally bypass the dry cooler and use the ground loop all by itself. So all summer long, when the air is warm enough, they're putting warm water into their ground loop to make sure that the ground around their bore field is warmer than the deep earth, essentially. Better than constant. If you want heating, you want something better than constant temperature from underground. You want warm temperature from underground. So moving along. So this is just kind of a summary, which gives some of the fundamental results from the 5 different multi-source approaches And the one that stood out to be the best in terms of initial cost and total cost of ownership over 20 years was the dry cooler with regeneration or preconditioning. A 28% lower initial cost than geothermal alone, and total cost of ownership, including electricity, over 20 years, which is 10% lower than conventional geothermal. Notice there's one here, the PVT had an initial cost which is actually higher than the baseline borehole approach, but the total cost of ownership is 7% lower. Now, PVT is kind of a relatively new technology, and if some company finds a way to build those in very large quantity and 20% less expensive, instead of plus 14%, the initial cost might be lower than the borehole only baseline design, and the total cost of ownership would also be much lower in that case, considering the electricity that is generated every year. So it's possible that with mass production, the PVT approach might be better than the bottom choice here, which has a dry cooler. Only time will tell. And anybody could look at the costs that the authors from Norway and China assumed for their system and put your own costs in there and see how that would change things. So moving along. Now, this is the same graph we looked at before, but in this case now we've got 4 simulated data points that we could put on this graph. So this is closer to the real world now. So the baseline design is the number of boreholes equals 6 conventional geothermal. Then they did an analysis of 5, 4, and 3 boreholes. So 3 boreholes is a 50% reduction, or it's only 1/2. Now, the case for numbers 3 and 4 actually had a slightly higher annual electricity use than did the conventional geothermal approach. The number 5 item here actually had a lower annual electricity use than did the conventional geothermal. And some of the other multi-source examples that were studied also had a lower annual electricity use than conventional geothermal. So moving along, I believe. So zeroing in now for some specific numbers for the for those 4 data points on that previous graph. These are the numbers that show for the case of 6 boreholes, and then the percentage cost reduction for the initial cost and also for the total cost of ownership over 20 years. So again, we see that cutting the borehole number down from 6 to 3 gives a very significant benefit in both the initial cost and the total cost of ownership. So moving along. So here's another example which would combine level 1 and level 2 into level 3. So this is an example where you can choose either the air source or the ground source, or you can do preconditioning from the air or solar block into either a cold ground loop or a hot or warm ground loop. You could have those ground loops combined into one also if you want, and then the valve V1 would only need to be a 2-port valve rather than 3-port. So that's a choice. But instead of only 1 pump and 1 valve that were shown by the recent paper, this requires 1 more valve to be added into the system to get the benefits of of level 3. So moving along to the next one, we're showing here the direction that water will flow in those valves when you have the different modes of operation. So the air source mode is, oh, by the way, the darkening of the triangles in the valves is shows the ports where water can flow in or out. If the triangle of the valve is not darkened, that means that no water can flow in or out of that port of the valve. So the air source mode allows water to flow from the heat pump down into the air to liquid heat exchanger and then back up through pump P1 and to the heat pump, but no water will flow into either ground loop. So that's the air source mode. If you want to have a ground source mode, and you want both ground loops to be in the system, then that's the top right example here. And the air or solar heat exchanger is bypassed with valve B2. The water bypasses that block and it only goes to the ground loops. If you only want one or the other of the ground loops, that's the bottom two block diagrams here. So I think we can move along to the next one. I'm trying to be quick enough so I don't run over time. So preconditioning or regeneration is shown here. So in this case, in all of these cases, water will flow through the air or solar heat exchanger, and it'll flow either into both ground loops or one or the other. So 3 choices there. Now you can also consider whether or not the heat pump is actually in use. If the heat pump is not in use, the compressor is off, then you're still be able to do the preconditioning here. Or you can have the heat pump on and have the connections as shown here. So instead of, then if we consider all of those possibilities, then these 3 blocks represent the possibility of 6 different modes. So combining that with the 3 modes on the previous slide, we might have 10 different modes of functionality for this system. And they will need to be studied to see which one is best to use at any given time. So it might be promising to go in that direction. So moving along to the next one. So here we're showing level 4 on the right-hand side. The far left example is a really simple block diagram of what we're calling level 1, either or. The middle example here, the dry cooler cannot connect to the heat pump. It can only do a preconditioning, in this case into one or the other ground loop. So that's what we're calling level 2. The right-hand block diagram is one step beyond level 3, what we're calling level 4. And that's explained a little further in the next slides. Go on to the next one. Okay, so I think these are kind of repeats anyway, so I'm just going to zoom through these and you can look at them and think about them, but these are the 2 opposite seasons, hottest summer day and the coldest winter night. So you're getting warm water for the heat pump from the hot loop when you need it, and you're getting cold water from the colder ground loop when you need that. Hopefully you can have the water cold enough to have a very long duration of free cooling, so-called, or bypassing the compressor in the heat pump. So moving along to the next one. So this shows what we're calling parallel mode. If you want, you can have some water coming from one of the ground loops and some other water coming from what we're calling here the above ground thermal exchange unit, dry cooler or solar thermal, whatever. You can have an equal flow from both of those blocks, and that's useful in the transition region between very cold and warmer. Go on to the next one. I'm going to go quick because these are all covered, I believe, in that 2022 presentation. So the middle example here is the simple air source mode. No water at all flowing through either ground loop. It's only in air source mode or solar thermal mode. Now, the right-hand example here is another version of what we're calling level 3. That is, it can do level 1, that is either or the bottom block or the right-hand block, uh, or parallel. Or you can do preconditioning also by not even requiring the heat pump, precondition from the bottom block into the right-hand block. So moving along. So this is a little bit more capable type of system where you can have solar thermal and a dry cooler. And this would be for a northern climate, I think, where the solar thermal does some real good. Uh, but the dry cooler can put cold water into the top ground loop for preconditioning. The solar thermal array can put very warm water into the bottom ground loop for preconditioning that. And these can all be what are called L-port valves, water source heat pump. Okay, moving along. So extending to more than one heat pump. Here we've got 15, arbitrary number, but the left-hand half of the screen is the same thing we've talked about already. We're showing a 4-port reversing valve in kind of the top center here. And that's one way to kind of equalize the benefits to all the heat pumps in the system. If you periodically reverse the flow direction in that primary loop, then if you reverse the flow once per day or once per week, then you'll have essentially the same average COP and capacity in all of the heat pumps. And if you don't do that, there could be a problem. However, if you have a system which has temperature measurement at all of those heat pump locations, temperature in the vertical flow direction, then you will know how much each heat pump, how much energy, thermal energy, each heat pump is either using or putting into the system. And so, and you know the temperature in and out of um, the heat exchange, let's see, not heat exchange, the Taco Comfort Twin T fixture that's shown there. That is a way to do what a pair of closely spaced tees will do, but it has two advantages over two closely spaced tees. You only need 4 pipe interconnections rather than 6, and you're also um, operating quite well whichever the direction of flow is. With 2 closely spaced tees, you have to pay close attention to the water flow direction in the primary loop. With the Taco Comfort device, it doesn't matter. So moving along, you could couple these primary loops together with a simple donut fixture, which could be made as a donut, as shown here at the bottom right, or it could be made with 4 T-junctions and 4 elbows, standard plumbing items. But basically, this is a way to make sure that water will flow through both loops rather than only one, if you have the same flow rate in both primary loops. If anybody wants to go into more detail on that, I would welcome them to let me know, and we can go into that as much as anybody cares. I'm not aware that anybody's done this, but it's a very simple way to, if you have a big heat source in one primary loop and you want to have that heat shared with another primary loop, this is a really simple way to do it. Moving along to the next one. So now what I'm imagining for the more distant future is to have perhaps each a block of homes um, in a city having a water pipe running around the block. So if you could drive your car around the block where you live, you can also put a water pipe around that block where you live. So every home has one water pipe running past it, and the heat pump in any given home can tap into it and either put heat in or take heat out, as long as the temperature in that loop is between maybe 35 and 90 degrees Fahrenheit. Um, you get efficient heating and cooling. So I think this is realistic. Now, a lot of blocks might have 30 to 40 homes, but there's no reason why they couldn't be all on one single closed loop where water is continuously flowing in that pipe at all times. Um, Now, this shows a hot loop on one loop and a cold a cold source on the other loop. It wouldn't have to be that way. You can have a cold and a hot loop on both of those loops, whatever. But regardless, if you have the donut fixture coupling them, then all the heat in one loop will be shared with all the other heat pumps in the other loop, and vice versa. All the cold in the right-hand loop will be shared with all the heat pumps in the other loop. I find that kind of interesting. But so moving along, I'm going to skip through this. This is something that's done in multiple locations in Denmark. It's a way to get very hot water available seasonally, heat it up all summer long, and bring it out to the homes all winter long. It's been done multiple locations. We know it works. So moving along to the next one. This is just a slight variation on that previous one, which might have some advantages, but it's been discussed previously, so we'll move along to the next one. Okay, this is a fairly new company in the Netherlands, and it has an interesting name, Hoko Stow Hot and Cold Storage. And they're doing heat and cold storage on a seasonal basis efficiently with a huge water tank that's buried in the earth, totally covered up. You would not even know it's there. So they've got solar thermal collectors here at the bottom left. They've got a kind of a honeycomb triangular structure made with aluminum tubing and pipe that they embed in the earth and covered up with earth. So moving along to the next one.
For your request, Gaylord, we have about 5 minutes.
Okay, I'm near the end.
Okay.
I'll try to hold it to that 5 minutes. Again, you can see the up-to-date information on Hoko Stow just by going to their website, hokostow.com. It might move into this country eventually, but I'm not sure about that. Move on to the next one. So if you want to store thermal energy underground, you can do it with water, just as the Hoko Stow example shows, but you can also do it with sand and gravel that is totally saturated with water all around the rock particles, sand or whatever. So silicon dioxide is much, much less capable for heat capacity compared to water. However, you also want a high density for that material. Silicon dioxide is much better than water for density. You also want high thermal conductivity to get that heat transferred where it should be. Again, silicon dioxide is much better than water for thermal conductivity. So I think a combination of water and sand or gravel particles is probably going to be just as good as water by itself. So that's what the next one shows, I think. Yeah, again, this was covered previously, so I'm going to just jump ahead beyond this. So how big does it have to be? These are some rough examples of how big a hemisphere would have to be if you want to do seasonal storage. This is a hemisphere insulated on the top, but not around the rest of it. So it's going to continually transfer heat from the surface of that hemisphere into the surrounding Earth. And this was also covered previously, so I'm going to just skip ahead from this. All right, this is something which was actually built, tested um, in England by a company called ICAX. And the top pipes, they've got two pipe layers separated by insulation. They're showing it on a highway here, but it could just as well be in a parking lot rather than a highway. So if they have black asphalt, let's say this could be an ice melt, a hydronic ice melt pipe array in a parking lot for a big building. If it's black asphalt, it's going to collect solar thermal energy to a very good degree on any hot sunny day. So again, it's a source for preconditioning into some part of the ground. They're showing another horizontal pipe array below the insulation that is a thermal store, as they call it. So you could have one of these to store heat underground. You could have another one to store cold underground, and use the level 4 kind of a block diagram to make it all work together. So the next one, this probably should have been the last one of the set of slides here. So I'll let you read this at your leisure whenever you want to. We're going on to the next one. So this shows a modified slinky loop trench. Instead of having only one slinky loop at the bottom of the trench, trying to get stable temperature, we're going to have two slinky loops in this same trench, one as close as possible to the surface and the other one at the bottom of the trench. The slinky loop at the top of the trench will get a functionality as a quasi air to liquid heat exchange and as a partial solar thermal collection. So imagine you have two or more of these trenches. If you have two of these trenches, you could keep the bottom of one cold, keep the bottom of the other one hot, and the two top slinky loops would be combined together to represent the air source functionality. So now instead of only two trenches, you could have 4, 6, 8. You could have slinky loops all over the Earth as much as is available there. And the only extra cost pretty much is the cost of the slinky pipe itself. And so to me, this might be a very cost-effective way to implement a level 4 type of configuration, and it might be one of the most cost-effective ways you could have to provide water to a whole lot of water source heat pumps. At least that's my thinking, and so it might be that the cost of putting in these ground loops will be less than the cost of the actual heat pump boxes in all the homes. So as right now, people think geothermal is too expensive because we don't want to drill those boreholes. No boreholes here. And I believe that's what people might find. The major cost is in the water source heat pump boxes themselves, rather than in what's buried underground. And since everything is buried underground, I believe you would call this ground source system, all fitting in with this association, in my view. So that's the end for me, I believe. Oh, well, there's a bibliography list here, the next one.
Let me, all right, great. Thank you so much. This was a fascinating presentation. Let me take a look at some questions. Do you have time, Gaylord, to stick around
Sure.
for questions? Okay,
I have
great.
all afternoon.
All right, let me take a look here. Let's see here. There's a question here about the slides being available. Are you willing to provide these slides to those who have attended? Okay.
No problem.
So if
Actually,
you're interested in the slides, just
Jeff, you
send
have
an
the
email.
slides. You have the slides, so you can
Yes.
share them. Yeah.
I just wanted your permission.
Yep.
So if anybody's interested in those, send an email to info@igshpa.org and we'll get those slides to you. And next question, will this video be available on the website? Yes, it will. Let me take a look here. Looks like we have some Q&A as well. Let's see, does dual source, both air and ground heat exchangers make economic sense for an average size single family home in central New Jersey? Are all the simulations intended for commercial sized buildings? How big should the building be for these schemes to make economic sense? Am I correct to assume that the single family home in New Jersey best solution would be either air source or ground source? So a lot of questions on there on that one from Tom.
I think when people get further into this, they'll find that multi-source is going to be uh, better for most single-family homes, as well as larger thermal energy networks.
Okay, good to know. They need to do their calculations, I guess, and find out. So
Sure.
Jonathan has a question. In a climate like the U.S. Midwest with much higher heating loads compared to cooling, but still need cooling, is there a good way to work solar thermal into supplement a loop field by only dumping heat into the boreholes from September to March, April timeframe?
You said only put it in September through March?
Well, the question was, this is a Midwest location that has still high heating loads, but also cooling loads. Is there a good way to use thermal solar in an application that does have a cooling load? I think is the intention here. And should they only be dumping heat in the September to March or April timeframe?
I would say no. I think you want to dump heat into the region you want to keep warm whenever the sun is shining and whenever the temperature can be warm enough.
Okay, so that's good.
Put your heat in there in June, July, and August, and then
When you've got a lot.
bring it out
Yeah.
in December, January, and February.
Okay, very good. Tom has a question again on central New Jersey. What's a better choice, ground source or heat pump? A ground source heat pump or air source, considering all the costs and comforts? Boy, that's kind of a loaded question.
That's what I tried to show. That is
Right.
okay. Well, let me add a little bit to that. If you want to really um, compare an air source heat pump with any other kind of a heat pump, that is conventional geothermal or multi-source, you have to ask yourself, uh, where will there be a crossover point where the total cost of ownership is the same for both? In other words, um, right now it's almost um, assumed that the initial cost of a ground source system is going to be more expensive than any air source system. However, it's also going to be assumed that the annual electricity cost for the air source system is going to be higher than the annual electricity for any other system, ground source or multi-source. So now you have to ask yourself, how many years of electricity bills will it take until the total cost of ownership for the ground source or multi-source system becomes better than the air source system? If you study that carefully and you find, well, the ground source system will eventually pay for itself if you wait 20 or 30 years, uh, you'll start to be saving money. A lot of people would say, I don't want to wait 20 or 30 years. I'm just going to pick the less expensive one. I'm going to put an air source heat pump. However, if we get to a point where a multi-source system can show that crossover point is 5 to 10 years, I believe at that point, a lot of people would say, I'm going to choose multi-source because in 5 years, I'm guaranteed to have always a lower electricity use, and the extra cost to do my installation is totally made up. So after 5 years, if my electricity use is forever lower, why wouldn't I choose that? You know, I
Well,
foresee the
fascinating.
day,
Oh,
pardon?
sorry. Oh, go ahead. Sorry.
I foresee the day when there will be more water source heat pumps sold than air source heat pumps.
Would love to see that. Well, in the
Yeah,
interest of time, I want to be respectful of everyone's time here. I really appreciate you speaking, Gaylord. This was a fascinating topic. And thank you so much for everyone joining our webinar today. The Dig Deeper webinars are always interesting, at least in my opinion. I'm a little biased here, but lots of good information. If you're interested in speaking, please submit an abstract. We also have advertising spots still available for Dig Deeper and Town Hall presentations. And I hope everyone has a nice weekend. Thanks again so much, Gaylord. And this video will be online in the next couple of days. Contact us if you'd like a copy of those slides, and we'll make sure you get those. Thanks, everyone. See ya.